Assalamualaikum warahmatullahi wabarakatuh. So we're going to continue with the introduction of the electric drives. Right, we have covered the some of the fundamental matters, which is the what constitutes an electric machine and why are there different forms of electrical machines. Okay, so I'm going to browse through. So we have covered this. Why are there different forms? And now we look into the variety of available machines. So the available machines have different types, different shapes, in different size, and it is actually characterized. They are actually characterized by number one is a power levels, torque levels, speed range, and positioning accuracies. So for the power levels, you can start with a microwatt, microwatt to 10 to the power of 9 watt, which is more than 100 megawatts, isn't it? So when we talk about small microwatt levels, you can think of the watch, your watches, right? So there is a small mechanical motor inside there. So it operates with a very small amount of power. So it's basically microwatt power. And then for a huge motor, industrial type of motor, it can go very, very high power there. And when we talk about torque levels, it can be goes down to micro Newton meter up to the 10 of 9 micro Newton meter. Spindle to the traction, electric traction, all the train traction. The torque level is very high. And then we can also look into the speed range of the machines, electric machines. You can start with a 10 revolution per minute, very slow rotation of the rotor, and you can go up to 500 kilo 1000 rpm, very, very fast rotor rotations. If you can think about a wind turbine, which is a huge wind turbine, so if you look carefully, the rotor, the blade rotates at a very slow rotation speed, isn't it? Rotational speed. So it is basically in terms of 10, in the range of 10 revolution per minute. But if you compare to the PCB spindle drilling, the PCB drilling is a very high speed machines. And of course, you can go up very, very high, 1000 of RPM per minute. And finally, positioning accuracies. It can go down actually to, the accuracy can go up to the nanometer, isn't it? Nanometer. For example, if you can think of the 3D printer, three-dimensional printer nowadays. We talk about the 3D in the IR 4.0. We talk about creating, the mold, and everything has been actually drawn by or created by the 3D printer. And we need a very precise positioning of the motor, and we use this motor that can go that can move very small length motor meter. Okay, and there is a graph there, which is the power versus the RPM, the speed of the rotational speed, RPM, revolution per minute. And next, we look at a variety of available machines. For example, again, for the power levels of microwatt to megawatt, hundreds of megawatt. For the induction machines, IM is induction machine power range. For small fans, it can operate from 100 to 500 megawatt. And for the fans, pumps, conveyor, escalators for industrial application, it can go up to 50 kilowatt. And again, for water pumping, coal cutting, which we need a very high torque, so it can go up to 500 kilowatt again. And for high speed train motor, 1 megawatt. And if you think of a high or a big, a huge warship cruise ship motor, then you can consider about 10 megawatt of machines, electrical machines, right? And next is machine topologies. Yes, we start with the first generation of conventional machine, and this is categorized by DC machine and induction machine, and finally we have this synchronous machine. The three conventional machines that we have covered that in electrical machines. I'm not sure whether it's semester 3 or semester 4. We have covered that, looking into the operation of DC machine, induction machine, as well as synchronous machine. And that is the first generation. When we talk about second generation, then we have this permanent magnet. This PM is actually permanent. If I can write, this is permanent magnet. PM is permanent magnet machines. This is under second generation, where we have a brush permanent magnet DC machine, as well as we have PM permanent magnet DC machines. And for the third generation, we no longer use the brush. We no longer use the brush, so it is a brushless PM DC machine, brushless PM AC machine, as well as the reluctant machines. And normally the famous or the regular reluctant machines is a type of switch reluctant machine, and it's also known as SRM, right? And these two generations is enabled by better permanent magnets. We have discovered a new technology on the permanent magnets. That's why it's used for the second generation. And for in terms of control reliant machines, basically this machine heavily dependent on the control of the drive itself, and that's why we have this third generation, because of the powertronic control and the control technologies that comes into the electrical machine and drive, and that's why we have this third generation, right? Next. Okay, so this is the photo of what is a first generation, second generation, and third generation. For the first generation, of course, for DC-DC, we have this uh, copper wire wound, as well as this we have this stator roto winding, as well as the slotted. This is a slotted roto stator, where we put a winding through the stator slot here, and it's a three-phase motor. And then again we have the AC induction machines there. So this is type of conventional machines. And when we talk about the second generation, we move into the permanent magnet. So this is the permanent magnet. We replace all the roto. We don't use electric, to winding to create the rotational magnetic field, but we use the DC, the permanent magnets, stick on the stator, and that is known as a second generation. And finally, for the third generation, we remove the brush. This is brushless motor, brushless permanent magnet motor. So this is under third generation, right? Second generation and conventional machines. Okay, so next, remaining questions. What do I need to know to use a particular machine? How can I analyze the method of working of a particular machine type? We will look at answering this question for each type of machine, the remaining part of the course. So some quick quiz just to refresh. What define output power? Can you define what is the output power, input power, power factor, and efficiency of a motor? You still remember what is the output power, a power factor, And then what factor can we use to find three-phase values from a single-phase result? If you have a three-phase system, what is a factor if you want to convert to from single-phase to three-phase? What is the ideal torque equation? What is the power related to motor torque? What is the power related to motor volume? So the definition of output power can be the power delivered to the load. And if you look into the input power, the total supply power required to operate. So that will be the input side, the amount of power that is available at the input side. And then output power is power delivered to the load. Of course, in reality, in practical, you have some voltage power loss from the input to the output, and that's all will determine the efficiency of the machines. And we also have this power factor. It is actually a proportion of input power that is converted into anything output and loss. Okay, so this is a power factor. If you look into the general definition of power factor, is actually the equation of the power factor will be the average power or the real power that delivered to the load, which is P divided by the apparent power, which is S. Okay, so the power factor, you have to be careful. Power factor is not always cos theta. It's not always cos theta. We have this cos theta only due to the voltage and current are sinusoidal. That is why we have power factor equals cos theta. But in powertronic, that's not the case. But the true definition, the actual definition of power factor is always average power divided by the apparent power, P divided by S. Okay, and I did mention what is efficiency. It's output power divided by input power. So what factor can we use to find three-phase value? It's a root 3, isn't it? So if you have a star connected system, the line-to-line voltage will be equals to root 3 of the V phase. And if you talk about delta connections, the current, the line current will be equals to root 3 multiplied by phase current. There are different between star and delta connection. What is the ideal torque equation of a motor? So there are a few equations that relates to the torque. One is a B multiplied by A pi dl multiplied by d over 2. B is magnetic density. A is the area. Pi d is diameter of the rotor. L is the length of the rotor. And again, d is the diameter. So if you rearrange that, you have to say that the torque is actually proportional to the rotor volume, and d squared over L is actually sort of relates to the volume of the motor. So the higher the volume, I mean the of the motor, you may have a high torque. You need to have a higher torque to move the rotor there. And how is power related to motor? Torque. Power is the mechanical power is always equals to torque multiplied by omega. Torque multiplied by omega. Omega is the angular or rotational speed or angular velocity, and the torque Newton meter. And how is power related to motor volume? We know that torque is dependent or proportional to the rotor volume, and therefore power also is proportional to volume and speed, right? So this is a relationship between power and torque, power and volume. Next is we look into the applications. Mostly nowadays, we have these electrical and hybrid vehicles being discussed, right? And why? Because if you use the electrical and hybrid vehicles, you actually improve the efficiency, and also you have the minimal impact to the environment. So we create a greener environment by using the electric motor compared to the normal combustion. The normal engine, it produce the smoke, isn't it? Yeah, so this is not good for the environment. Then that's why you move into the electrical and hybrid vehicles. And then we have a few types of machines can be used for traction, for the traction, for the motor, for the car. The first one will be induction motors, brushless DC, as well as AC, and the switch reluctant motor. And a demanding torque speed characteristic and operating environment. So if you want to design, you need to look into the what is the torque required, as well as the torque speed characteristic, as well as the operating environment. So all right, so let's look at the range of application for electrical machine in cars. So we start with the normal, I mean the conventional car that we had. Actually, we already apply the motor inside our car nowadays. For example, for electric windows, we use the small motor there. For electric seats, right? If you want to move backward, frontward, your seat, you use the motor inside. And in terms of the locking system, the central locks of your car, also use the small motor there. Power steering, the analog gauge, which is the RPM, which is the speedometer of your car, also use the motor there. And then we have a turbocharger. Traction drive motor is actually more on the hybrid electric car. And we have the alternator, sort of a generator there. And we also have this starter. So we already implement, or we already apply the motor inside our conventional car. But we talk about electric and hybrid vehicles, it's more on the traction drive. Typical requirements for the traction of the motor or of the car, normally the speed can go up to 14,000 rpm. From the normal 3,000 rpm, it can goes up to 14,000 rpm. And from the previous lesson, we know that the power equals to torque multiplied by speed. So output torque can be vastly different depending on position or the speed. So the output torque will be dependent on the speed, and the torque also dependent on the volume. And there is another equation that describe the torque, which is torque equals to 2 multiplied by volume of the motor multiplied by magnetic density, as well as the area of the motor. Motor size can also vary radically from 5 to ratio from above. Right. Now let's look into the specific example or the specification of a motor. In US, in America, they introduced this Freedom Car 2020 policy. So whereby for US greener policy environment, they introduced the Freedom Car 2020, and they specify the specification for the electrical machines. And this is the spec which is come through the Freedom Car, come with the Freedom Car specification. The rated power is 30 kilowatt. And just to give you some idea what is the electric in the electric drive for the electrical and hybrid vehicles. The rated power can go up to 30 kilowatt. The peak power 55 kilowatt for 18 seconds. The peak torque is 200 Newton meter for 18 seconds. And the rated speed is 2,800 rpm. Maximum speed, again, 14,000 rpm. And they are operated from a DC voltage of 200 to 450 volt. So you have to have a series of a battery bank, a battery that will provide 325 volt rated. This is a rated value, 300 over a voltage. So you must have a rechargeable battery to be connected in series to produce this 325 volt. And maximum back EMF at maximum speed is 600 volt. This is the back EMF of the motor. And we talk about the machine current, can be goes up to 400, very high current, for maximum current of 400 ampere. And then we have a machine diameter, machine length of 25 cm, 20 cm. The volume must be lower than 9.7 liter, cannot be greater than 9.7 liter. The machine should be less than 35 kilogram, and it has to be liquid cooling system. Coolant temperature can go only up to 105 maximum, and the efficiency should be 95%, above 95%. Preferred non-rare earth IPM or magnetless technology. The unit cost is only about 275 per unit in quantities of 100,000. I'm not sure about this, but it says that 275 ringgit per unit. I'm not sure what cost is this. Okay, no worries. And that is a electric car applications. Now we look into the generation application, generator. So most form of conventional renewable generation include electrical machines. They use or apply electrical machines. As fast rotation as possible. P equals to torque multiplied by omega, but application dependent. Right? Normally it's fast rotation as possible. You want to make it as fast as possible, but that's not always the case, because sometimes you may have your generator or the main rotor, the main prime mover, they call it prime mover. The prime mover is in terms of wind. So wind usually rotate at very low speed. Wind turbine usually rotate at very low speed. So conventionally, we in UK and Malaysia, we have the steam turbine. Right, in the coal plant, we use the coal to have this steam coming out. And for steam turbine, for typical two pole, we have a 3000 rpm. Why? I hope you still remember that for the synchronous speed, the equation should be ns equals to 100 multiplied by f s divided by p, isn't it? So your fs here is 50, your p is 2, and therefore you have this 3000 rpm. Right, and that is the speed of the synchron of your rotor. But for hydro or wind speed, the rotational speed, the blade of the rotor of the motor of the wind turbine rotate with a very slow motion rotation. Okay? So you can go down to a few 10 rpm. Moment. Okay, let's go further. Range of application for generation: conventional for fuel burning, generally coupled directly to steam turbine to convert thermal, mechanical, electrical energy. So this is a fuel burning, or coal. We use coal to create a fuel burning. And then we have a wind fuel or coal burning, right? And number two is wind, usually uses a gearbox between rotor and machine to increase rotational speed. As I mentioned just now, the rotation speed of the wind turbine is very slow, so you have to use a gear to speed up the rotor so that you have a higher speed frequency. So the faster the rotation, the smaller and lighter and usually cheaper a generator can be. And in terms of hydro application, it has some multiple solutions. Some use low speed turbines, for example, a water wheel. So it rotates very slow. You talk about the underwater current. So they rotate with this very slow speed. But generally use water pressure to produce high speed. So if you use a water pressure, you can increase the speed. And commonly use a medium speed 1000 rpm reaction turbine, such as a Francis turbine. So you have to Google what is a Francis turbine there. Steam turbine based generation typical requirement, high efficiency conventional generation. Of course, we use a steam turbine, high efficiency, high reliability with maintenance, and also as well as high power. The typical constraints, system cost and lifetime. This is a constraint. We talk about system cost and how long it will survive. Starting and synchronization needs. This is a very challenging constraint for the synchronous machine. You know, how to synchronize that with a 50 Hz line frequency, as well as a control, idling operation, and fairly ideal environment, custom design, space without type, weight, size limits. And now we look into the renewable generations. Just now we have this conventional generation. For a renewable generation, for wind turbine and wave, underwater wave turbine there. Rapidly expanding application. This is a expanding application. Different types of machine can be used. We can use a doubly effect induction machines, wound synchronous machine, and permanent magnets. Reliability and maintainability are important properties, especially for machine used in offshore generation. Of course, we must make sure that the motor is a very high reliability with low maintainability. Yeah? So, because we can't afford to do maintenance as frequent as we can at the offshore, right? Wind generator typically requirements very high reliability, high efficiency, high power level, low maintenance. And typical constraints will be weight and size, location, environment, grid connection. Operating environment is hostile, challenging to maintain, and generally remote. So this is why, the main constraints of wind generator is a hostile environment, challenging to maintain, generally remote. All right, in the terms of industrial drive, for standard drives used in a huge range of industrial application, wide range of types, but generally standardized and mass produced. So don't worry about that. A huge range of system available dependent on application area, but typically not application specialized. So the design can be general and you can use it anywhere. Not application specialized. So it can be generally auto that. Range of application for if you can think about industrial drive, it usually used for fans, for pumps, machine tools and manufacturing, automation and robotics, conveyors and movers, test equipment, transit system, as well as the lift. That's it for the industrial drive. Again, for industrial drive, typical requirement tend to be standard size, which is 90 kilowatt. Oh, very high, isn't it? It's based on grid supply. Can have 50 or 60 hertz, 3-phase or single phase, 400, 480. Given speed, induction machine types can operate at other speed, but given speed is generally optimal. So normally it will be specified what is a given speed for your motor. Right, typical constraints for industrial drive environment range from standard to fully enclosed for hazardous, corrosive, and clean environment. Efficiency standards and for the frame size standardization. This is the only constraints of the industrial drive. Now we look at the marine applications. How we use the machines, electrical motor in the marine application is increases usable space, decouples engine speed from propeller speed for faster dynamics, optimize power use, several propellers supplied from one generator at low power, and there's no gearbox. There are usually no gearbox. Again, for marine application, range of application for electrical machines, podded thrusters, okay, podded thrusters, and then we have a decoupled generation, and a smaller loads, which is a bow thruster or pumps, control of steering, as well as emission management. So this is example of podded thrusters, and we look into the typical requirements: robust and reliable, long lifetime, highly efficient, controllable. Sorry, work with large mechanical depths, and typical constraints will be operating environment, limited access, seawater, corrosive substance, and direct concentration versus traditional type. All right, not only for marine, on the sea, in the sea, okay, we also have this application on the air, which is more electric aircraft. So we need to have a reduced weight because we apply the aircraft, and as well as the high energy should be increased. Okay, and we need a highly reliable and fault-tolerant machines because when we talk about aircraft, it flies up there. So we need to have a system which is highly reliable, and we must to make sure that there is no fault at all. We must keep the minimum, because it's very risky to fly an aircraft. Very risky, isn't it? And then we have the electrical machines used for electrical actuations, generation, the ECS, environmental control system, fuel pumps, thrust, and reversers. Again, for more electric aircraft, range of applications for electrical machines, generation for system load turbine connected. We have this APU, auxiliary power unit. So if there is something wrong with your engine, then the APU also will take over, and as a standby. We have this wind turbine to give static power in emergency ram air turbine. And for the control surfaces, it has to be rudder, aileron, and flap. And for the landing gear, so how you control the extension and control of the landing gear. And finally, for green taxing, again, US has this electric green taxing system, whereby when you want to move your aircraft on the ground, we don't use from the main engine, right? We can also introduce these own electric machines that control the tire of the wheel of the aircraft, and this wheel will drive. Will transport the aircraft for the taxiing purpose. Taxiing is you pull, or you make sure that your aircraft park at the correct positions. Okay, so this is a green taxing. Starter generator typical requirements: small and light, high efficiency, high reliability. Again, starter or generator of small electric aircraft: small and light, high efficiency, high reliability. Typical constraints: should have an environment up down to 20 degree cold to combustion temperature, normal to 1/4 of the atmosphere pressure. And for the mounting, in engine challenges of size and shape, because it has many size and shape, so the mounting is another constraint. And finally, we have the size, weight, and reliability. So it's the typical constraint for a more electric aircraft because it flies in the air. And now we talk about linear transit and launch. Again, linear motors accelerate a vehicle along a track. So how linear motor difference from the rotational motor? Linear motor brings one position to another position, isn't it? If you want to transfer, we talk about the train. Okay, so this is a linear motor. Normally used in amusement rides and for UAV aircraft launch. We talk about aircraft launch on the battleship, on the warship, right? We have this aircraft launch. So it has the motor that will speed up the jet so that it can fly. Ideal characteristics for a launch machine: a high force density and short-term output. So it has to be a burst, high force density and short-term output. And then high reliability and robustness, high efficiency and power factor. And range of application for electrical machine can be for the linear transit and launch, can be a baggage transport. So the baggage transport uses the linear transit, linear motor, and as well personal transport. I'm not sure what is this, hyperloop. And for the amusement ride, launch, assisted aircraft takeoff, and the projectile launch, and aircraft launch system. Typical requirements: very high short-term thrust, because if you want to launch it, you need to have a very high thrust, isn't it? Very high short-term thrust, so that you can launch the aircraft from the warship, from the battleship, isn't it? High reliability and fail-safe, efficient, high power factor, controllable. So for typical constraints, power supply size and availability, payloads limits, limited space and mass. And finally, this is some example. You can I try this YouTube? Try to play this YouTube video on the testing on the aircraft. Is it still there?
Can I have one honey golden apple pearl? Wait, no. I want a brown sugar pearl. More sugar, white colored jelly, maybe less.
Ever wondered how the U.S.
There
Navy
you
makes
are.
sure their carriers can fling fighters like this?
Okay, so testing an aircraft carrier catapult, they call it catapult. Look at that. Okay, so that's a testing system. Okay, that's it for the video. So you can repeat, watch again, right? So mainly was the introduction, just give it an introduction to the machine and applications, so on and so forth. Okay, Assalamualaikum warahmatullahi wabarakatuh. Thank you.